Good afternoon, all. Thank you so much for joining me for this EC590 seminar. Today, I will be talking about brushless Doubly-fed reluctance machines and a new type of architecture known as switched architecture for wide spin range applications. So first of all, I'm going to introduce you to brushless Doubly-fed reluctance machines, or in short from BDFRM. Then I'm going to talk about the power converter sizing for this BDFRM. We're going to look at the conventional versus the switch drive architecture for this type of machine. Then we are going to do the comparison between a brushed version and a brushless version, how the power converter sizing varies between these two machines, and I'm going to talk about my current research work. So first, moving on to the introduction of the machine. How does machine looks like? So the stator core is pretty much the same what you have in an induction machine or in a permanent magnet synchronous machine. So you have stator slots. In one slot, you have one of the windings known as primary stator windings. On the second side, you have another winding called secondary stator winding. The rotor is pretty much similar to what you have in a synchronous reluctance machines, that is of reluctance type rotor. And since the rotor does not have any windings, you don't need any slip rings, therefore the machine is brushless. If you combine all the terms together, you get brushless Doubly-fed reluctance machine. So why do we need this type of machine? So this machine actually came into existence in this wind power applications. So people first started using this asynchronous or synchronous machine. And for connecting the machine to the grid, we required a power electronics over there. In this case, the power electronics has to be rated for the full system power. So if your machine is rated for, let's say, 1 megawatt to 5 megawatts for this wind turbine applications, your power converter has to be rated for that much amount of power. Same goes for your filter as well. So both your filter and power converter has to be designed for your system rated power. That's why both your weight and cost of the system is gonna increase. So then what we can do to reduce the power converter sizing? We can actually use Doubly-fed induction machine in this type of applications. What this does is in a Doubly-fed machine, you have two windings, one on the stator, another on the rotor. Your stator winding is directly connected to the grid. So you can see the stator winding is directly connected to the grid, whereas your rotor winding is connected to the power electronics and then to the grid. This rotor winding actually carries only a small percentage of the rated power, that is roughly around the slip percentage. So let's say if your slip varies from 15 to 20%, your power electronics has to be rated just for 15 to 20%. So you're going to improve your efficiency, you're going to decrease the cost, you're going to decrease the weight of the system. What are the disadvantages using Doubly-fed machines? Since there are windings present on the rotor, you need slip rings, you need brushes, and that's why the reliability of this system decreases. Especially for systems such as offshore wind turbines and aerospace applications, we cannot have a system which is less reliable. That's why we try to implement this brushless Doubly-fed reluctance machines for these type of applications. So you have two windings, the primary stator winding directly connected to the grid, as well as the secondary stator winding, which is connected to the grid via this power electronics. And since the secondary stator winding only carries a part of the only carries a fraction of the rated power, the power electronics is reduced. You have a brushless operation because of the reluctance rotor. The main problem with this type of machine is the reduced power converter rating is only for a limited speed range. So if you want to go from 0 to rated speed, you will require a power electronics which is of the rated system power. And the main point why we went for brushless Doubly-fed machine was to reduce the power electronics. But we won't be able to do that for an application which requires a wide speed range. So in comes a different type of architecture known as switch drive architecture. So what we do in this architecture is that instead of directly connecting your primary stator to the grid, we instead have a transfer switch between this. So what happens in that is that in high speed, very similar to what we had in a conventional drive architecture, we connect our primary stator to the grid or the three-phase AC supply. But in low speed, instead of connecting it to a three-phase AC supply, we can either short it so that this machine can behave like an induction machine, or we can actually connect a DC supply across the primary stator winding. In this case, this is going to behave like a synchronous machine. So the main the main difference between a switch drive architecture and a conventional drive architecture is in the low speed region. In the low speed region, we either short the primary stator winding or we connect a DC source across the primary stator winding. Why do we do that?
Wait,
yeah.
Can I ask a question?
Sure.
So if you short that winding,
yeah.
you're still having rotating field, otherwise the machine's not
yeah.
going in it.
Yeah.
So if you have rotating fields and
yeah.
short windings, you have short currents.
Yes. So this is very similar to what you have in a wound rotor induction machine. So you can similarly treat that this is as your stator and this is as your rotor windings. So the rotor windings are shorted, whereas the stator winding is still connected to this three-phase AC grid.
Even though they're both in the stator?
Yes. So I'm not going to talk about the torque production, how the torque is being produced in this machine. That itself is a very complicated process, and if I mean it will take. Okay. Okay. Yeah. So what happens is that on a stator winding, you have two windings which have different pole pairs, different frequency. Why do we do that? It's because if they have similar frequency and similar pole pairs, then they're going to have a transformer action. Like what happens in a transformer, you have two windings. One winding is going to induce EMF in the other winding. So first of all, the pole pairs and the frequency is different for these two windings. Why do we have this reluctance rotor over here? Because of this reluctance, some of the magnetic fields which are being produced by the secondary winding are gonna get coupled to this primary stator because of this reluctance type. So what is happening is the torque is still being produced by the coupling of these two stator windings, but it is being produced because of the reluctance present in this machine. I think that's. And I mean, if you want, I can send you some documents related to this, but the torque production is a lot more complicated. The definition is still the same. You still need two rotating magnetic fields to couple to each other to produce the torque. But how it is produced in this machine is very different from rest of the machines. But what happens in low speed mode is that this DC, if you short these windings, this behaves just like an induction machine. If you connect a DC supply, this behaves like a synchronous machine. Why do we short it? We'll look in the next slide. So actually the converter voltage required is actually proportional to this over here, omega P minus omega R for Doubly-fed machines. What is omega P? Omega P is the grid frequency, omega R is a rotor speed. Everything is in per unit. So if you look at the converter voltage requirement for a conventional BDFRM architecture, so let's say if your rotor speed your rotor is rotating at the grid frequency, so the converter voltage required would be 0. But as we move on to low speeds, since your omega R decreases, omega P is still 1, you are still connected to the grid, your converter voltage requirement increases significantly. But for a switch BDFRM architecture, if you short the windings in low speed, both your omega R and omega P now decreases to, so omega P goes to 0, omega R reduces as you move on, as you lower the rotor speed. So you can see the converter voltage requirement for a switched BDFRM architecture reduces significantly as compared to a conventional one. But all the graphs shown here are for ideal machines, the machines which don't have any leakages, no resistances at all. But as we all know that the real machines are going to have some resistances, some inductances, some leakages. So how do we decide the power converter size for a real brushless Doubly-fed reluctance machine? How do we get the, so the next topic is going to be how do you decide the current rating, how do you decide the voltage rating for a real machine and using this switched tribe architecture. So the machine which I have chosen is 1.5 kilowatt machine. I had the ratings for both the primary stator and the secondary stator windings. I had the voltage ratings, the current rating, the pole combination, the rated speed and everything else. So how do you decide the power converter sizing? Let's go about this one. So the first task for me was to compute the current rating of the power converter. This is actually achieved in the high speed mode. Why do we do that? It's because in the high speed mode, the torque capability required of the machine is much higher. We are actually using a fan type load, and for a fan type load, the torque actually is proportional to the speed square. So as you go on to the higher speeds, the load torque requirement is much higher as compared to the low speed mode. And that's why you need to maximize your torque capability of the machine in high speed mode. Since the torque is proportional to the currents which you are feeding via the power electronics, you need to decide the current rating in the high speed mode. So in high speed mode, my design objective was to maximize the torque capability of the machine, but the constraints were both the stator current limits. So the red curve over here shows the region in which I can operate. So this curve shows the current limits set by the primary stator. The blue curve over here shows the current limit set by the secondary stator. So I can only operate the regions which are common to both, that are shown by ABCD region. So on the y-axis we have converter d-axis current, on the x-axis we have converter q-axis current. So ABCD is the region in which I can operate, and now I need to maximize the torque of my machine. The torque of a machine is proportional to the q-axis current. So C point actually is gonna give you the maximum positive current, maximum positive torque. A point is gonna give you the maximum negative torque. All these points can also be plotted in a different way over here. On the y-axis I have torque, on the x-axis I have q-axis current. So A point is gonna give me the maximum negative torque which the machine can produce, and C point is gonna give me the maximum positive torque which this machine is gonna produce, and these current it's gonna give me the q-axis as well as from this graph the t-axis current. So for this q-axis, what is the t-axis current? I can get my d and q-axis, and hence the current rating of my power converter. What happens in the low speed mode? So the low speed mode decides the voltage rating of your power converter. So the design objective in the low speed mode was to minimize your converter voltage. But what were the constraints? Now the constraints were again your stator current limits, but another constraint was now your primary stator flux. What happened in the high speed mode? Your primary stator winding was directly connected to the grid. You did not have any control on the flux in the high speed mode. But in the low speed mode, you can actually control whatever flux you want to put in the machine. So again, in the low speed mode, I need to minimize my converter voltage based on these constraints. Yeah, so these are some of the expressions which I used for writing my converter voltage in D and Q axis. I just needed to minimize this function under those constraints. After I had done that, I achieved these two graphs. So this blue line over here shows the voltage requirement, your converter voltage requirement for your low speed mode. This red curve shows the voltage what I have got in the high speed mode. The point where they intersect gives you the transition speed. So this is the speed where you need to move on from high speed to low speed or vice versa. So you can remove the remaining parts which are not required. And this graph actually shows you the converter voltage requirement according to your whatever the rotor speed, and the maximum voltage whatever is required gives you the converter voltage. This is actually just shown for maximum positive torque. We need to do this again for negative torque and then compute whatever the voltage rating is required. So all this analysis was done for switched drive architecture. Now let's look whether or not we were actually able to reduce our power converter for a switched drive architecture as compared to a conventional one. So if you look at the conventional BDFRM, and if you look at the converter voltage required versus the rotor speed for a conventional BDFRM drive versus a switched BDFRM drive, we get around 55% reduction in the voltage rating of the converter. And the main reason is because in the low speed mode, we are not connected to the grid, but we are operating with the DC source. Same goes for the reactive power handling capacity by the converter. So for a conventional BDFRM drive, so the red curve over here, the red line over here shows the reactive power being handled by the converter. The blue line over here shows the reactive power being handled by the primary stator, and the green line is the net reactive power handled by the machine. So if you look for the conventional BDFRM drive versus for a switched BDFRM drive, there is around 67% reduction in the power handling capacity of the converter. So your converter size it's definitely going to reduce for a switched BDFRM drive. Interestingly, the maximum active power handled by in both the cases, in both the BDFRM, in the conventional BDFRM versus the switched BDFRM, this did not change. This analysis, I compared the switched architecture versus the conventional architecture for a brushless Doubly-fed reluctance machine. Next, I'm going to show you the comparison between a.
You said for low speed you're using a DC source.
Yeah.
Where do you get that? Is that like a startup battery pack or something?
Yes. We're gonna use a battery pack over there. And the voltage requirement in this case, what I got. So how do you compute like what's the DC voltage is gonna required? That again is we're gonna compute this input DC voltage and primary stator flux in the low speed mode. So I need to minimize my converter voltage. So what's the DC voltage which minimizes my converter voltage, but under these constraints. And for this machine, the obtained DC voltage I think was around 40 volts.
So the assumption would be that you use a battery to start up
Yes.
and get to speed, but your primary operation
Yes.
is fixed speed, or is within that top.
It's within, yeah. So within.
Not necessarily. So you can create this DC bus using
Okay.
And you can operate within the entire speed range from 0 to all 1.5, no matter where you end up with it.
Probably slightly lower efficiency.
In what sense?
Well, if you're using the passive rectifier, you would lose a little bit.
And
Probably not much.
Well, very good question. The reason the passive rectifier is going to supply is only the stator loss. So when you are operating, exciting it with a DC current, all that power converter supplies is I square R loss, nothing else. There is no energy conversion which is being handled by the DC source. Okay. So that converter power rating is super small compared to the overall machine size of the converter size.
Yes. Yes. So in this low speed mode, you will always be connected to the DC supply, the primary stator. But your secondary stator is connected to the grid via power electronics. And all the power which is actually being fed to the shaft is going via that power electronics and via the secondary stator. Okay. So your primary stator in this region is carrying very, very less amount of power.
It's only I square R loss with supply.
Interesting.
Yeah.
Cool. Thank you.
Yeah. So now I'm going to compare the switch drive architecture for a brushless machine as well as for a doubly-fed machine. So Professor Banerjee actually did this switch drive architecture for a doubly-fed machine during his PhD. I'm doing this switch drive architecture for the brushless doubly-fed machine, and we're going to compare like what is, yeah, let's see. So this is a switch doubly-fed machine drive. So what we have over here is you have a stator winding connected to the grid via the transfer switch. So again, in the low speed mode, you're going to short it or you're going to connect it to a DC source. And in the high speed, you're going to connect it to the AC grid. Whereas your rotor winding is connected to the AC grid via this power electronics. Whereas for this switch BDFRM drive, what we don't have any windings on the rotor. You have two windings on the stator. One of the primary winding is connected to the grid via this transfer switch. Again, in the low speed mode, we short it or we connect it to a DC source. In the high speed mode, we connect it to a AC source. Whereas your secondary stator now is always connected to the grid via the power electronics. So in the end, like what's the difference? You are actually moving your power electronics from your rotor winding and you are feeding it to a stator winding so that you don't need any brushes. So now let's look at what is the size, like what is the size of power electronics for a DFM drive? What is the size of the power electronics for a brushless doubly-fed machine drive? So what we observed was because of the high leakages present in the brushless doubly-fed machine, the reactive power demand in a brushless doubly-fed machine was significantly higher as compared to a doubly-fed machine. Now that amount of reactive power you can actually either feed via primary stator winding. In that case, the power factor of the grid was gonna go down. But if you say that no, I'm gonna keep the power factor of my primary winding to be of my grid or my primary stator winding to be around 0.9 or 0.8, then all that amount of extra reactive power has to be fed via power electronics, and that's why your power electronic sizing for a brushless doubly-fed machine increases significantly by around 45%. So in the end, it's again like if you want to go for a brushless operation, the power electronics is going to be higher for a BDFRM machine. What I'm doing currently is I'm developing a control architecture for the drive. So here we have a very basic control loop over here, some controllers showing the current controllers, the speed controllers, the flux controller, and your reactive power controller for the machine. I'm going to finish this pretty soon. I'm also trying to analyze what happens in case of a sudden change in load torque. So let's say you have a bird strike on your propeller blades. How it's going to impact your machine, how you're going to control this one. But the most important point which I'm focusing on is how do you go about reducing the leakage inductance in a brushless doubly-fed machine? Because if you can do that, if you can reduce the leakage inductance, you can actually improve your power factor, you can decrease the power converter size, and you can increase the power and torque density of the machine. Yeah, that's pretty much it. Thank you. So any questions? Yeah.
Can you go back through? You had a couple of slides on the power. It looked like reactive power and real power.
Yeah.
I got a little bit confused.
Yeah. Yes. So this is your reactive power. So what is happening is the red line over here shows the reactive power handled by your converter or the secondary stator. The blue line shows the reactive power being handled by your primary stator. And the green line over here shows the net amount of reactive power being fed to the machine.
Okay, so all of these are just are reactive powers.
All these are reactive powers. One shows for the primary stator, one shows for the secondary stator, and one is the net reactive power.
Do you want to mention why there is a discontinuity?
Yeah, yeah. So if you look around, there's a discontinuity at around 0.5. So 0.5 was my transition speed moving from low speed to high speed. Why is there a discontinuity? Is because in the low speed mode, I am operating at a low torque. So in this region, I'm operating at 100% of the rated torque, but in the low speed mode, I'm operating at 75% of rated torque. Why am I doing so? It's because I'm using this machine for a fan load, and for a fan load, again, as I mentioned, the load torque is proportional to the speed square. So at low speeds, I don't need that much amount of high torque. So I can operate at around 50%, around 75%, depending upon the applications. And because of the change in the torque in the low speed and the high speed, there's a discontinuity over here.
So you're assuming that you have a fan load.
Yes, this was done. This was done for this turbofan applications for the propeller blades. So this is a project funded by NASA, and they wanted us to do this for aircraft propulsion applications.
Cool.
Yeah.
So then you have apparent power graphs also?
I have reactive power and the active power. So you can, so if you want to convert, these are the active power, yes. So if you look at, so again, the red line shows the active power being handled by the secondary stator or the converter. The blue line shows the active power being handled by the primary stator, and the green line is the net active power being supplied to the machine. And this is for the switch drive architecture. And if you want to compute the ratings of the machine, that's going to be what is the maximum amount of power. And that's actually the same in both these cases, because the maximum over here is being decided in the high speed mode. In high speed mode, conventional and switched architecture are basically the same. The reactive power handling capacity is actually decided in the low speed mode. And that's why there's a difference. Yeah, welcome. Yeah, okay, thank you. Oh, sorry.
Probably pass the attendance again since people have arrived.
What is this?
So there's forward, reverse, and your laser pointer.
Okay.
If you stand over there, I'll be able to get you the camera.
Okay. Okay, good afternoon, everyone. Today, I will be presenting a technique for maintaining zero voltage switching across the full duty cycle range for FCML converters using dynamic level selection. So the application that we are targeting is solar microinverters for high voltage thin film solar panels. These solar panels can produce anywhere from 100 to 200 volts DC instead of the typical about 48 volts DC. So this way, instead of needing both a buck and a boost stage, we now only need a single buck stage. This allows us to reduce the size of the converter, and if we also can improve the efficiency of the converter, we can actually put the converter either in the junction box of the solar panel or eventually embed the converter in the panel itself. And we want to use a high power density topology in order to get this reduced converter. So the flying capacitor multi-level topology is a very high power dense topology. It is, since it's a multi-level topology, the dV/dt across the inductor is reduced, and this allows us to reduce the size of the inductor. Additionally, there is a frequency multiplication at the inductor, and these two things allow us to have an n-1 squared reduction in the inductor size, allowing us for the smaller converter that we can embed in the panel and saving cost. Another advantage of the FCML topology is the reduced voltage stress across the switches. Because these flying capacitors are at voltages that are a fraction of the input voltage based on the number of levels, the VDS across any of these switches is also a fraction of the input voltage. So for the 5-level case, the VDS across these switches is only 1/4 of the input voltage. And in order to take advantage of this high power dense topology, we also want to switch faster so that we can even further reduce the size of the converter. But as you switch faster, you have more switching losses. And one way to mitigate this is to use zero voltage switching. If you have 0 volts across the transistor when you switch, you have 0 losses in that switch. And to get this 0 volts across the transistor, we can actually use the parasitic capacitance of these transistors. So if we look at the switch pair closest to the inductor, we can analyze how we actually achieve 0 voltage switching. The analysis is the same for any switched pair, but we will look at this one. To get ZVS on the low side switch is relatively easy because, as you can see, during the dead time before the switch turns on, there is a highly positive inductor current that can be used to discharge this capacitance, and you can quickly discharge to 0 volts before the switch turns on, therefore getting 0 voltage switching. However, when we look at the high side switch, this is much harder because, as you can see, during this dead time before the high side switch turns on, you actually need a negative inductor current so that you can discharge this parasitic capacitance to 0 volts before the switch turns on. And in order to get this negative inductor current, this means we need a large inductor current ripple so that the inductor current goes negative. And if we look at the typical 2-level buck case, this is the inductor current ripple over the full duty cycle range. And you can see that the minimums are only occurring at 0 and 100% duty cycle, which is at the edge of your typical operation region. So maintaining enough inductor current ripple in the middle of the operation range in order to get that negative current to discharge the high side parasitic capacitance is easy for the 2-level case. However, when we move to higher number of levels, this becomes more of a challenge. If we look at the switch node of the FCML, as mentioned before, there's not only an effective switching frequency at this node, but there's also an effective duty cycle at this node. For example, for the 5-level converter, if you have a converter duty ratio of 12.5%, at the switch node, you actually see a duty ratio of 50%. These two things affect the inductor current ripple, and you can see that the magnitude of the inductor current ripple as you increase the number of levels actually reduces. This allows us to reduce the size of the inductor. But this also comes with a negative in that we have minimums that are occurring not only at the boundaries of operation, but in the middle of our typical operation region. So if we zoom in on the 5-level case, in order to achieve for a constant output current at a fixed switching frequency, there is a minimum inductor current ripple needed to get that negative current that discharges the high side parasitic capacitance. And you can see, and that's plotted here on the red line, and you can see there are duty cycles which fall below this minimum inductor current ripple. This means we cannot achieve ZVS for these duty cycles. One way that we can address this is by adjusting the switching frequency. By using variable frequency control, we can decrease the range of duty cycles which fall below this minimum inductor current ripple. So we can have a wider range that we can achieve ZVS. If we now plot the switching frequency needed to maintain this constant inductor current ripple for the constant output current, that is what's shown here. And however, we cannot switch our converter arbitrarily slow, and because there are limitations on things such as inductor saturation or voltage ripple on the flying capacitors. So there's a limit to how slow we can switch. And as you can see, again, there are duty cycles for which we are below this minimum, and we can again not achieve ZVS. So we can look at converters with a different number of levels. So if we look at the 4-level case, we can see that at the same duty ratio, we can achieve the same inductor current ripple and operating at a higher switching frequency. This means that if we can operate the 5-level converter as a 4-level converter in these ranges, we can be operating above this frequency limitation. And if we apply this dynamic level selection across the full duty cycle range, we can maintain ZVS across the full range. So how do we operate a 5-level converter as a 4-level converter? Well, let's look at the control signals. The FCML topology typically uses phase-shifted PWM, which means that each of the switch pairs are phase-shifted from the other by a value that's determined by the number of levels. So for the 5-level case, the phase shift is 90 degrees. And also, for this constant inductor current ripple, the switching frequency is also determined by the number of levels. And when we want to operate as a 4-level converter, first we need to control the 2 middle switch pairs, S2 and S3, in phase with each other so that we can freeze the voltage on capacitor C2 so it is effectively not there, and these 2 switches are acting as a single switch. Then the phase shift and switching frequency are updated in accordance with 4-level operation. So now the phase shift, instead of 90 degrees, is now 120 degrees with the 2 middle switch pairs in phase with one another. But again, another challenge is that we cannot immediately switch from a 5-level to 4-level operation. And this is because, as mentioned before, the voltages on these flying capacitors is determined by the number of levels. So between the levels of operation, the voltages on these capacitors is different. And the middle switch pairs were chosen to be controlled in phase so that the difference between the voltages on these capacitors between 5 and 4 levels is minimized. And so now we look at how we can bridge the gap between the different voltage levels in the 5-level and the 4-level case. One way we can use is the voltages can naturally balance. However, this is a slow process, and the more cycles that the converter is operating unbalanced, the more harmonics that are in the converter, and also there's higher stress placed on the transistors. So we can use active balancing techniques to speed up this rebalancing process. So to actively rebalance these capacitors, we need to look at the regions when these capacitors are either charging or discharging. So here in D1, this is the subperiod when switch number 1 is on. In this state, capacitor C1 is discharging. In D2, when the 2 middle switch pairs are on, C1 is charging and C3 is discharging. Similarly, when switch number 4 is on, C3 is charging. So when we want to transition from 5 to 4 level, we want to increase the voltage on capacitor C1. So we want to increase the time that we're spending in D2 and decrease the time that we're spending in D1. Similarly, when we want to decrease the voltage on capacitor C3, we want to increase D2 and decrease D4. And then after time of active rebalancing, the converter then transitions to typical 4-level operation with the middle switch pairs again in phase with one another. So to demonstrate achieving ZVS using variable frequency control and dynamic level selection, we built a 5-level hardware prototype with specifications for a 200-volt high voltage thin film solar panel and we used 100-volt GaN devices on a single-sided PCB for bottom side cooling using a cascaded bootstrap for a gate drive supply. Here's an annotated picture of the converter with power flow from right to left. So you have the input capacitance followed by the switch pair, flying capacitor, switch pair, flying capacitor, all the way to the filter inductor at the output. Here we're showing ZVS being achieved for the 4-level case and the 5-level case. These duty cycles that we are showing were chosen specifically to demonstrate the need for dynamic level selection. So if you remember this plot, for the 5-level case, ZVS cannot be achieved at 25% duty cycle, and for the 4-level case, ZVS cannot be achieved at 33%. So we're operating at these duty cycles, but on the other number of levels. And you can see here that the inductor current is going negative. This negative current discharges the high side parasitic capacitance, therefore giving us ZVS. And this is also evident by the lack of overshoot on the switch node voltage. Here is showing our transition from 5-level operation to 4-level operation using active balancing. And as you can see, the voltage on C3 is decreasing, the voltage on C1 is increasing to steady state 4-level operation. What we are currently working on is improving the active balancing region and the level transition, because the results presented today were done for a fixed switching frequency. However, as discussed, we need not only dynamic level selection, but also variable frequency control. We also will be testing at higher duty cycle ranges and eventually have a closed loop control. Today, we have discussed the difficulties of achieving ZVS across the full duty cycle range for FCML converters, and we have proposed a new technique in order to correct this through use of variable frequency control and dynamic level selection. And we built a 5-level hardware prototype that demonstrates ZVS at duty cycles for which a fixed number of levels cannot achieve ZVS. And we've also shown level transitioning with active balancing. Thank you, and I'll take any questions.
How long does it take for the active balancing to take effect?
Right now, it takes just two cycles, but that's only for the single case that we've tested so far. But as we test higher duty cycle ranges, we can see how that changes for different duty cycles, and potentially we can decrease. If it takes longer, we can decrease that time.
How long does it take to do the not active balancing, just the passive balancing?
Can I go to like the last slide, 28? Is that possible? But it's a hidden slide, so I don't think you can see it on the presentation. Can you just click number 28, please? This one right there. Oh, sorry, 27 maybe? Sorry. Okay, so this is comparing natural balancing and active balancing. So natural balancing, and for this duty cycle range, takes 400 microseconds, whereas active balancing is 50 microseconds. So you can see it's a drastic difference between using natural balancing and active balancing.
I'm going from 4 levels to 5 levels? Have you, because there might be some, you're going to lose some voltage off of your capacitor,
Mm-hmm.
I would assume.
We've also done 4-level to 5-level transitioning. Just in this presentation, I only showed for 5 to 4 level, but it seems to act very similarly to this case, just in the reverse direction.
Have you done a startup as a 4-level and then a transition to 5-level?
No, our main operation is going to be in the 5-level case, because with a higher number of levels, you have a higher efficiency because your switch stress is reduced and you have a smaller dV/dt. So we want to operate mainly as the higher number of levels and only occasionally move into the 4-level operation. Does that answer your question? I mean, sort of, but I guess you're asking if we start as a 4-level. No, we haven't done.
I guess when I look at your graphs, you're saying that one of the main problems is you have this switching stress in these kind of null points, right?
Mm-hmm.
So when you look at the edge of the graphs, right, in the far left and in the far right, you can see that the 4-level comes down there's more area in the 4-level. Can we look at one of those graphs? Yeah. So there's more area in the 4-level. I guess this picture is showing that you're using a 3-level the 4-level rather than the 5-level because of the switching stress. If the black line is what you're using.
Yes.
At 0 duty cycle.
At 0.
Almost 0.
Yeah.
Near 0 duty cycle, this is showing that you're using the 4-level.
Yes, but these are atypical regions of operation, so we haven't tested those regions yet. We're focusing mainly on the center region.
Okay.
So we have not tested that yet.
Okay. Thank you.
Causing the duty cycle to need to be changed.
So when you convert from DC to AC across the full line cycle, you need the full range of duty cycles. Or for other applications, if you have a wide input or output voltage, you're going to have a wide range of duty cycles for which you want to be able to, if you want to use ZVS, you want to be able to do ZVS across your full operation range.
So, very interesting work, first of all. Secondly, so if you increase, so now if you can achieve ZVS, does that mean you can switch your switching frequency even higher?
Yes, so that's the goal. We want to switch faster so we can have smaller converters, more efficient converters. So we need ZVS to do that.
So now you're switching at 40 kilohertz?
No.
What's your switching frequency right now?
Right now we're operating at 50 kilohertz for just base testing, but that's because we're just operating above this frequency limitation line for our specific converter. Sorry. One more. This at 50 kilohertz, so we're operating here so that
You're saying always above this 50 kilohertz.
Yes.
But right now your switching frequency is constant.
It's constant, yes. So that's what we're currently working on, is being able to change that switching frequency. Because as you can see here, if we want to operate at the 4-level, we really need to be operating at a higher switching frequency.
50 kilohertz is 20 microsecond once after.
Mm-hmm.
Right? Yes, 20 microsecond. And you are achieving your active control in 50 microseconds. Correct?
Yes.
So if you increase your switching frequency, do you think that's going to impact your active control time, or is it going to stay constant? Or is it going to be affected in any way? Will that impact anything?
It might, because these, well, I'll just use this one, because in our active balancing, we are changing the amount of time that these duty cycles are, the on time of each of these switches. So if we're switching at a higher switching frequency, like the time of this duty cycle will be different. So yes, it could affect how long the active balancing.
So will it help you or will it be against you? If you go on higher switching frequency versus time it takes to go for active balancing?
It should hurt us because we are.
Basically, you're slicing that time event now, so your switches are going to see much more transients, will be under stress for a longer duration of time, more during switching operations. Is that correct?
I think so.
So is there a way to get out of this problem, or what's the strategy there?
So just to be clear, even when we're switching between the two levels, we're not violating our switching ratings because we rate everything for the 4-level voltages anyway. And so even when we're out of balance, we're still within that rating of Vn over 3 as opposed to Vn over 4. So we still have more switch stress than we'd like and than where we were when we're balanced, but we're not actually above what we rated it for. Now, we still, whether we can maintain ZVS during that region and how long it takes, like those are some things we need to work out. And some of that's dependent on how well we implement the active balancing. But going to high-speed operation is definitely where we need to go. Right now, we're low speed because it's easier to show the concept off.
Now, this is a very interesting concept. And how high do you aim to go? Like, what's the switching frequency you want to go?
It really depends. I mean, this right now is very much showing off the concept. We've implemented similar ZVS type converters where the switching frequency, what Derek went up to, I want to say 300 kilohertz, or no, it was like 150 kilohertz on a higher number of level switches.
But again, it was active balancing, and it was a switching between two
So
levels.
he was not doing that.
Only ZVS.
Basically, he ran into the problem that we're solving, where he said at a certain point, I just can't get ZVS, so I'm only going to operate here at the peaks. We're now saying we can go out the full duty cycle range, and then we'll try to work back to where he was as far as the higher switching frequency and a much smaller inductor.
Very good.
Is there any certain reason why you choose 5 to 4 level, 4 or 5 levels? Why capacitor?
Several reasons, none of them super quantifiable. Using the 4 and 5 levels, it's easy to demonstrate this concept because you don't have as many switch signals that you need to control, especially in the active balancing region. And also, this allows us to use the 100-volt GaN devices, which have very low RDS(on), so that will improve the efficiency of our converter. Any other? No.
Just to add, you also did the math and showed that the change in the capacitors was smaller for 5 to 4 level than a 6 to 5 level, if I remember right.
6 to 5 level.
Because you actually end up getting a larger capacitor swing in the 6 to 5 level than you got the 5 to 4 level.
I don't remember, so I don't want to say yes. But yeah.
One more question. How do you think that you want to get rid of C2? Like when you are changing to 4 level, you don't want to use C2 anymore.
Yes.
What was the rationale behind that?
Because if we freeze the voltage on this capacitor, basically the delta V between the overall switches is minimized. So C2, there's 0 delta V needed, and for C3 and C1, this delta V is the minimum based on like whether we operate 4 and 3 in phase or 4 and 2, like all combinations. This is the combination that gives us the minimum delta V. So this will give us the smallest amount of time for active balancing. If you need, that's the least amount you have to change by.
Okay, and one more question. This is so interesting, that's why there are so many questions in my mind. Sorry about keeping you guys waiting. But say, for example, you have been operating on level 4 for a while. So C2 is kind of sitting idle. Suppose it's doing P over 2, but it's going to discharge. And it's going to fall off its voltage level because it has its own losses, measurable. How long do you need? Is there a time restriction on how long it can operate in 4 level? Means can C2 be 0 and can you pull it back up to 5 level later on, or doesn't that happen?
That's FCML magic. No, I don't know.
That is something we need to investigate more.
Is it a relevant question, first of all?
Yes. What we've seen is that even when we sit there and operate in 4-level mode for indefinitely, there's either through parasitics or blind luck on just probably the parasitics, it stays at roughly half that voltage anyway. And some of that kind of makes sense, right? You've got some kind of a capacitor divider going on there with the 2 capacitors on each side. But whether we want to rely on that or whether we want to find a better way of maybe occasionally you pulse that on and maintain that is something we'll have to figure out moving forward. For our 60 hertz applications, you know, I'm not too worried about it in that case. Like I wouldn't expect the parasitics to change that much. But even in that case, you know, we have changed the voltage a little bit. Actually, no, it should still be at half. So for the 60 hertz application, I think we'll be fine. Whether you want to operate there indefinitely, that's a really good question.
Okay. Thank you.
Would operating in 4-level change the expected lifetime of switches or capacitors and make it uneven between all the different components?
Well, so all of the components are sized for 4-level operation because we want to pick the worst case when choosing all these components. So if it's a balanced operation, then yes, you have more switch stress on these, but it's within the specifications of those components.